Okay, hi everyone. We're going to deal today with low degree testing. And the subtitle of today's lecture would be the locality of the Reed-Muller code. So if you see, it's already quite analogous to what we had yesterday. Yesterday we talked about linearity testing, and it corresponds to the Hadamard code. And today we're talking about low degree testing, just higher degree polynomials and linear functions. And they would be correlated with, they correspond to the Reed-Muller code, which is by far my favorite code. And I think the structure that you see here is quite fantastic. So let's just start by a quick recall of what happened yesterday. So yesterday we defined this notion of linearity testing. So what was linearity testing? We said we're getting some query access to some function, which could be any function, on n variables over a finite field, and we want to know whether this function is linear or not. And we want to do it using a very small number of queries, namely just a constant number. Maybe just probe it at 3 different places, so 70 different places, but like a constant number of locations. Okay, all nice and well, but this is impossible. And the reason why that seems impossible is because there can always be this chance that we don't probe a certain location, and that location would differ from linearity. So we focused on the notion of property testing, where the goal was to say, is this function linear, or is it far from being linear in fractional distance or Hamming weight distance? Okay. So we had this nice algorithm in which we looked at a triangle. So what is a triangle? We picked some x, we picked some y, and then we looked that we made 3 queries, f of x, f of y, and f of x plus y. And we checked that the relation that, f of x plus f of y is equal to f of x plus y. That is a local constraint. And then this idea of having a different characterization of linear functions, not only as, just a function which is a linear combination of the variables, but rather a function which satisfies this local condition. This is what allowed us to get a proof, to get a test. And we had a test which proceeded in these 3 steps, which I won't remind you right now, because we're going to have the exact same 3 steps in the analysis of the low degree test. So in some sense, we've done already, the hard work is behind us. And what we'll do now is we look at a richer structure, and we'll design, a similar test, but one which relies on the richer structures of low degree polynomials. And then we have an analysis which kind of follow these steps. And what I'll do in this lecture is I'll focus on, the conceptual differences and what's interesting. And you see, this is a much more interesting proof. So let's see. Let's start by talking about low degree testing and what does it even mean. So, because in linearity testing, we had this function from Fn to F, and the goal that we had at the time was to say, if this is a linear function, then we'll make these 3 queries or 10 queries, and we reject with probability 1. And if it is far from being linear, say, 10% far from being linear, then we'll kind of say that we wouldn't say that we accept unless with some probability of half. And, if you want to get better probability, you just repeat this test several times. This was a 3 query test. Okay, so the goal of low degree testing would be exactly what you'd imagine. We'll have here an input some finite field. We'll have the number of variables. So far, this is exactly as it was in linearity testing, but we'll also have an additional parameter, d, which controls the degree, right? So in linearity testing, d was always 1. So now we are looking at this generalization. So we have this oracle f, or like this function f, and recall that the way that we probe it is we choose some vector x, and then we get the value f evaluated at x. Okay, and similarly, or exactly as before, we want to say if our function happens to be a low-degree polynomial, a polynomial of degree at most d, then we'll accept this probability 1. If it is epsilon far, we'll reject this probability, say half or something like that. Depends on exactly what we mean by far. Okay, so first, pedantic but important question to ask, which is exactly the question that Amit asked right now in the chat. Thank you, Amit. What does degree D mean? So there are two, standard definitions of degree. We have a total degree, right? So a total degree is, we might have this function, I don't know, x, y plus x squared y to the third, and we say that the total degree here is 5, like, determined by this thing. And we also can have a notion of individual degree, which we're kind of like saying for each variable, what is the highest degree that will that we raise the variable. So just to say, when we're talking about total degree, if we restrict D to be 1, then we get exactly linear functions, because it means that each term that we have is of degree 1, so it means that can only include one variable. And if we look at individual degree, then we get multilinear polynomials. So maybe we'll have this x, y term, which is still linear. So we'll focus in our setting on total degree, and the main reason is because it's quite straightforward, and it's an exercise. I think you might even do it in one of the worksheets. So it's a very simple exercise that if one has an access to total degree test, to infer from that an individual degree test. So in some sense, it's like quite a simple exercise to be done. And so we'll focus on the slightly harder case of low degree. But regardless, in most applications that we have to PCPs and locally testable codes and anything of this sort, like the difference is kind of marginal. Okay, so we're dealing with total degree. And what we'll do is we'll do it in 2 steps. The first step would be to kind of first look at low dimension, or namely dimension 1. So we'll just consider a function, f from f to f, right? So we fix n to be 1. So this is like the simplest thing. And the reason why we'll do that is because that's like the clearest and cleanest setting. And as you can imagine, since we want to get to the general case, then this next step would be to generalize it to multivariate polynomials. And the cool thing about it, and this is a nice phenomenon, is that we'll actually spend 90% of the time looking at the univariate case, but we'll do it in a way that such that extending it to the multivariate setting would be something which is nearly trivial. So, while we wouldn't do the straightforward algorithm that one can do in the univariate case, we'll do something more sophisticated, but something more sophisticated that would later easily generalize. Okay, so that's the definition of the problem. Any question? Does this make sense? Okay, good. So if something is not clear, please feel free to interrupt me. But it is very similar to what we did yesterday, just with a higher degree. Okay, and before we're diving into algorithms and into mathematical analysis, I want to tell you about low degree polynomials and why polynomials are, at least to me, this magical mathematical object. This is something that Oded Goldreich told me, I think, a decade ago, and as with the years, I just like learning just to understand how amazing the properties are. So let me kind of start with the absolute basic. So, consider univariate polynomials. Just, some your favorite. Let me, just write something. X plus x to the fifth plus 7x to the 8th. So consider polynomial over some finite field f. So polynomial in like univariate polynomials, they satisfy something which is really nice, and that is that they admit interpolation. So what do I mean by interpolation? We can fix any set of d plus 1 points, and that determines a polynomial. And so, we can say maybe, so I have this function and I know what is the value. It's like you see in high school when you take some parabola and you fix 3 points, and then you know that's like the entire value of the parabola everywhere. Similarly, when with low degree polynomial, you fix d plus 1 points, and that fixes the value of the function over the entire domain. Now, this innocent looking phenomenon, which is kind of like equivalent to the number of roots that a polynomial of degree d has, it's actually what makes polynomial a good code. So what do I mean by that? You can always do something along the lines of, you evaluate your polynomial at a certain number of places. In this case, the places that I, colored by green. And then you can consider your function over a much larger domain. And the values on this larger domain are being determined uniquely. And they behave pseudo-randomly. They are, so each two polynomials are very far from each other. So what this tells us is that if we look at the collection of all univariate polynomials, this is a code, in the sense that each two univariate polynomials of degree d differ from each other in like a huge fraction of the domain. Okay. So now that's univariate polynomials, that's kids' play. And now we're trying to consider polynomials in higher dimensions. So now we just consider some function, and let's say of total degree d. And here's something much more interesting is happening. But maybe before I say that, I just want to maybe make one picture. So when I said low degree extension, I meant that you can kind of like take your favorite value x, evaluated on d plus 1 point, and then you can consider it over an arbitrarily large finite field f, and all the values here would be uniquely determined by the green values, by this d plus 1 point. So what will happen in the higher dimensional case? So we'll have this cube. So let me say, first of all, what this cube is supposed to mean and what I'm writing here. So, before, when I looked at the one-dimensional case, I kind of like drew the evaluation of polynomials just as a line, where I'm just like putting point after point after point, right? So I have here, maybe this is confusing, so let me erase this. Okay, so what I had is like, this is one value, this is the second value, so it's a line. And and then the places which are not green are kind of the low degree extension. Similarly, you can consider a polynomial in two variables and just write the evaluation as a 2x2 grid, right? So you'll have, here you'll have f of, maybe this would be f of 0, 0, that, when f of 0, 1, f of 0, 2, f of 0, 3, and we just like stack them in a grid according to the first coordinate and the second coordinate. So you can do this in 3 dimensions, as I drawn before, and you can do it in n dimensions. Okay, so this cube, imagine that each point in this cube corresponds to some vector x over which we can evaluate the function. And the value of the cube at this point is the value of the function, right? So maybe the best way to see it is like consider this point z. So we actually write there in the cube this f of z. Okay, so this is the picture that I want you to have. And now something amazing is happening. So the first thing, which is amazing, is that we can show that this entire cube this is a very good, this is like a good code, in the sense that if you take any two low-degree polynomials and evaluate them over this entire domain, if you evaluate them of the entire cube, then they would be very far from each other. Okay, this is nice. But it extends far, far, far beyond that. So for example, we can take any affine subspaces and even more, and we'll still get code. So what do I mean by that? Like, if I take any line in the hypercube, then this line would be another good code. And the reason why is if you take a polynomial and you restrict it to a line, this is just, taking the polynomial and evaluating it by the equation of a line. So in some sense, the degree remains the same, and this is still a low-degree polynomial. But you can also evaluate a polynomial over a plane, and this would still be a good error-correcting code, in the sense that the plane would have distance between any pair of polynomials. And this extends to curves, this extends to hyperspaces, this extends to manifolds. So in some sense, what's really rich about polynomials is that not only they are pairwise far, but also an incredible amount of subsets of the polynomials are still code. So it's kind of a fractal-ish type of code. And this is a question that I've been looking at for I think about 10 years, of trying to find any other mathematical object, complex as it might be. It could be a simplicial complex, it could be something that we derive from tensor codes. Nothing has this structure, nothing at all that I managed to find. So it's quite a unique and interesting thing, and it's funny that it comes from such a basic notion as a polynomial. And you'll see that this would, in some sense, enable all of the power of PCPs and this local to global phenomena, because the moment that you get this sweet structure, then you have a point. Maybe this point is corrupted. So yes, let's just take a random line through that point. But maybe the line is problematic, so let's take a plane, and maybe we want to capture several points at one time, so let's take some curve and interpolate, and so on and so forth. And we'll do lots of interesting things with that. And what we'll do today is we'll see that, suppose that you get this cube, this polynomial in n variables, and you want to know whether this polynomial is a flow degree or not. Then instead of reading the entire thing and checking, it would actually be enough to look at a random line, just like look at some line in the space, look at the restriction of the polynomial into a line, and notice this is something of like density, which is, tends to 0 with respect to, like, it doesn't have volume, it's just, a one-dimensional line. And if the line would be a good, a low-degree polynomial, then the entire object would be of low degree. And if the line would be a low-degree polynomial, then the entire object with high probability will be, of low degree. And so Amit is asking now regarding whether this is only true for fields or sometimes rings. So that's a good question to ask, and one can interpret it in many ways. Like, for example, you can ask, what about algebraic varieties, and what about algebraic function fields? That there are different settings in which you can consider polynomials or Laurent polynomials, where you can have other degrees. And in some settings, we do have similar settings. So maybe when I'm saying, polynomials, it doesn't mean necessarily in the strictest sense that I write here, but this interesting phenomenon seems to happen when you, take combination of variables in low degree. I hope this is clear. So, this interlude is just like to give you some intuition, and now we're getting into the actual math. Okay, so let's see how we can do this, this test for univariate polynomials. So we're starting with this idea, which I mentioned before, that d+1 locations determine a polynomial uniquely. So here is a very naive test. Or in fact, maybe let me ask you. Suppose that you are getting, some polynomial, and you want to know whether this polynomial is of low degree. Do you have any suggestion how I might be able to test that using the property that is written on the board?
Test at like D+2 locations and see if it's consistent?
Yeah, absolutely. As Wilfred said, the idea would be to say, well, let's take D+1 locations, and then let's take another location. This D+1 location, maybe the green points here, this would kind of determine a polynomial. And using this polynomial in my head, I can evaluate it everywhere that I want. So I check another position, and I check whether it would agree, the interpolation of this D+1 points would agree on another point. Yeah, that's a natural thing to do. Now, we don't want to pick this point deterministically, because maybe we'll have a coincidence, but if we pick this point at random, then, things should be good. So this is indeed what we do. So we sample a random point, and then we query the function, in some arbitrary D+1 point, and at the point that we care about R, we interpolate the polynomial, and we compare this point. Yeah, as simple as it gets. So what would be the query complexity here? So just D+2, right? Like the D+1 point that we need to interpolate an additional point. And all this is non-adaptive, like everything is selected, in advance, and everything is nice and simple. Okay, so let's see what will happen with completeness. So if the function is a polynomial, then definitionally all points will agree. So, I can check it on any point and I'm happy. So because all of the points will agree, and notice that I will use this notation throughout, that this tilde above, this is the interpolating polynomial. So, if the interpolal polynomial is exactly the same as P, then they agree everywhere and everything works trivially. Alexandros is asking whether it's enough to take D+1 points deterministically and just the extra point at random, and yes, that is enough. Yes, and this is actually what we're doing here with these points. And to continue with soundness, this is actually also very simple, because we have the simplest bound that say, what is the probability that we will accept? It's a probability that the interpolating polynomial will agree with a certain point. So if the function differs on, 10 points, then we always have this bound that, 1 minus the distance of the function from being low degree, we will manage to catch a bad point. Okay, so this is completely, straightforward to do. And we're getting this query complexity of OD points. And, you can ask, is that interesting? So if the finite field F is huge, then this is very local, right? Because in some sense, this is like this D points, it's just a small fraction of F, and then we're saving something. However, in most settings, we actually don't want to blow our encoding by a lot. And we choose D and F to be very similar. And then in some sense, this is extremely expensive. Because if F is twice the size of D, then in order to run this test, we're actually paying a lot. And I see a question regarding checking that the finite field is, so I'm not entirely sure. So sure, okay, so there's a question regarding the size of the finite field, and absolutely, like definitionally, we will only, I should have wrote that, we will only consider like finite fields which are larger than the degree. Otherwise, this entire thing would get degenerate. So in some sense, this is like a parameter known to the algorithm. Thank you. Okay, so just to finish the previous line of thought, so we need, so the query complexity of O of D is what we get from this test, and one can easily show that any test for univariate polynomials will require this omega of D. And the way to see that is, if you ever heard about the notion of k-wise independent distributions, then this would be trivial. And otherwise, the point is that if we are just evaluating a polynomial at less than d+1 points, then we can always tweak the rest of it until we are fixing d+1 point. Like, think about your one-dimensional polynomial here. If you only set part of the values but not all d+1, then you can still have degrees of freedom to go pretty much as far as you can. And so, one can take this intuition and formalize it quite easily and show that this test is in fact the absolute best that one can achieve for testing low degree. So now, of course, why aren't we done? We have like the ultimate test for testing low degree univariate polynomials. The problem is that if we try to take this approach and generalize it into higher dimensions, then we'll get into a very bad situation. And the reason would be that, if we go back to the, maybe just 1 second, to the example, to this, to the picture here, then it would mean that if we do it in higher dimension, we need to query the entire cube, which is something of large volume. Whereas we want to only do, something tiny, maybe, just like something which is negligible with respect of the entire number of points, like a line or a plane or something of this sort. Of course, you'll see this all, stated more accurately, and so it would make more sense. So, yeah, okay. Guess I included this drawing for that, anyways. Okay, so is the basic, like, does that make sense? The basic test?
What do you mean by non-adaptive?
What I mean by non-adaptive is simply that the queries that I'm making to F, the points that I look at, they do not depend on one another. So it's not that I query the first location and then I see 7, and based on that I'm choosing which other point, but rather I'm picking all of my queries to begin with. And the reason why to care about this non-adaptivity is because it's a desirable property, and later you see that we'll need it for some transformations and things like that. So this is just a side comment. Thank you.
Okay. Thank you.
Okay, so what I want to tell you about is a different approach where we'll get roughly the same thing, or maybe even worse, and we'll do a whole lot of work for doing that. But the benefit of that is that it would allow us to generalize into higher dimensions while maintaining fantastic like locality. So, let's focus here for simplicity on the setting of finite fields, which are prime fields. So we have this, finite field f of p for some prime, p, which is at most p+2, at least p+2, sorry. And if you remember, what was the key step, the key idea in setting of linearity testing? Well, it was to have this duality, to have a different representation of linear functions that would allow these local constraints. And in the linear setting, this was, like taking f of x plus f of y equals to f of x plus y. And in the setting of degree d polynomials, we'll have something very similar. But because it's degree d, rather than having 3 points, we'll maybe have like d plus, it would be a constraint involving d+2 points. So, okay, here I'm defining just a bunch of constants. And what I want to ask of you is like not to think too much about these specific definition. I mean, I'm writing it here for the sake of being explicit and to say that we can easily find them, but let's think about that there exists some constants that would satisfy what we want. What we'll have is the following thing. We'll have this lemma, which is equivalent or analogous to what we had in the linearity sense, which allow us to move from, a linear function is, a linear sum of the variables versus, function which always satisfy x plus y equals x, f of x plus f of y. So let me break down this thing into something which would make sense. So first of all, this whole bunch of notation here, it just means, if I have a low degree polynomial, right? So this is just saying f is low degree. And the local characterization that we'll have is exactly the rest, what we have here. And it would mean that we'll have this linear combination of values of f that has to sum to 0. So it's some sort of a linear constraint that the function has to satisfy. And at the risk of boring you a little bit, I want to stick a bit more and kind of like say exactly what this means. So, we have our constants, and let's not worry about them too much. These are some constants that satisfy this relation. But essentially what we're saying is that for every value a, it's a finite field. So, just to demystify it, f of p is like nothing more than the values 0, 1, 2, until, p minus 1. And so it means that we can start at any point, 0, 2, 7, 14, whatever we want, and look at all of the subsequent values. So, we can start at 7, and then we look at 7, 8, 9, 10, and 11. And we just look at the evaluation of the function on these consecutive points, right? And somehow the magic of flow degree, like the structure of flow degree polynomials tells us that, you can have a linear combination of f1 plus f2 plus f3 plus f4. If you weight it correctly, then it would always be 0, right? It's a nice property. And, let's see, this a little bit of intuition why this holds. So there is a proof, and you can see it in the notes. It's a bit cumbersome, but I want to just communicate like the main idea there. And I'm supposed to bore you with a tedious induction just to show you the idea. And if anyone has a problem with, the full proof, just let me know and we can add that. So the point is that let's try to see what this means and do it in steps. So first of all, let's focus on this setting. So that. Okay. So let's focus on the setting that d is equal to 0. Right, so what does it mean d is equal to 0? We have these coefficients here, and if we plug in the values, then we get that we get only two constants, c0 and c1, which are equal to -1 and 1. And so if we plug it in this equation, all we're getting here is that minus of fa plus f of a plus 1 is equal to 0. Now, does that look somewhat similar to something, the most fundamental object in analysis?
It's the derivative.
Yeah, in a very, very degenerate sense, right? I mean, it's kind of, I'm looking at f of a plus 1 minus f of a divided by 1 minus 0, or by a plus 1 minus a. So, fine. So we have this thing, and then let's see what happens if we do it for d equals 1. So we get these values -1, 2, and -1. And this will amount to having, this linear constraint, right? Like this would just plugging in this value translate to this linear constraint. And it might seem a bit ugly or random, but if we reorganize it, then, you get the derivative in one point and the derivative in another point. And also, if it makes any, if it looks familiar, this 1 and -1 and this kind of thing, this is kind of like, sign alternating Pascal triangle, and it naturally corresponds to polynomials. So in fact, when we do the induction, we'll keep having lots of these derivatives. And, it's a very simple proof to do, but just a technical one. And maybe to say something, so remember that last lecture I told you about like the slick and elegant Fourier analytic proof of linearity testing. I like to offer a bounty that, if anyone can give me, a real intuitive explanation of why that proof holds, then for me this is something I'd be happy like to buy you coffee or something along these lines. So this coffee trophy also extends to this magic of polynomials. So I've done this proof, I showed it at least 5 times in class and stuff, but I still don't see this inherent reason why polynomials has to satisfy it. So if anyone has an insight, I'd be very much interested in hearing about it. But it holds. Okay, and this could lead us into a new proposal, a new way of dealing with things. And before we make this proposal concrete, there is a question that I need to ask. And okay, so before in linearity testing, we had this global characterization of the function versus a local characterization that only involved 3 points. Here we have a global characterization which involves d points, and we have a local characterization which also involves d points. So why? What do we gain by doing this? How is that at all local? So I see in the comments, I think you might be on point. I'm not sure I followed. So let me just say my interpretation of that. So in the univariate direct sense, this is indeed nothing helpful. But because you kind of look at this thing and you have d points, and you can use these d points to interpolate and get values here. But the moment that we're going into even bivariate setting, so let's see what happens. So we have here, so here this was, maybe just to make it, this was d plus 1, and that is p, which is the prime, the size of the field. So when we look at 2 dimensions, we can write here d plus 1 and d plus 1, and here we'll have p and p. So what we'll be able to do is that in higher dimensions, the constraint will still only involve d points and not d, so the size of the input here, the size of the information is d plus 1 squared. And when we deal with n dimension, it would be roughly d to the n. Whereas the constraints that we'll have here will persist being just with respect to d. They will not, d will not grow in dimension. So what would it mean is that the higher the dimensionality of the polynomial, the more local the constraint is. And if we have a polynomial in log n dimension, then it's enough to look at a very, very, very tiny amount of points. And that's the main intuition. But again, it would all be done more accurately. So yeah. So just to say, this gives us a very natural way of having a new, different type of a test. And what the test would be. So just exploring, maybe I will not do that because of this. Okay, so we'll take some random point, r, and then we'll take f and just query it in consecutive points, f at r plus 1, f at r plus 2, f at r plus 3, until f at r plus d plus 1. And we'll check if this condition that we proved that we've shown in the lemma holds or not. Right? This couldn't be more analogous to what we've done. And this is a beautiful proposal. There's only one tiny problem with it, which doesn't work. Unfortunate, but luckily it's easily fixable. So first of all, I want to ask you a question. It's not an easy one, but just curious to see if one can see that, which is what could possibly break here? I mean, how, the reason, so as Ida said, indeed, yes, it would be the soundness that would break. Completeness would definitely work. But I want to even delve even deeper. So, what happened in the previous case with linear functions? We had this saying, a function is linear versus it satisfies these conditions regarding triangles. And we had this nice notion that the distance, the Hamming distance of a function from being linear corresponds to the number of bad triangles. This is kind of a robust condition. It's kind of it scales gracefully with it. And this doesn't necessarily hold. So try to see if you can find a counterexample where you have a function which is half far from being a low degree polynomial. So it's you have to change at least half of the coordinates. let's maybe say without loss of generality, you have to change the first n/2, like the first half of the coordinates in order to make this thing a low-degree polynomial. Yet this test will succeed with very high probability. Any ideas?
You can maybe put, you can take a d-degree polynomial and then put 0 in the first half or something like that.
Yeah, fantastic. So this is, you know, it's exactly this idea, which I'll explain, you know, in more detail, but it's actually an important idea because it repeats quite a lot. It's the generical example that we'll see in list decoding and things that we'll see later. So just to say, what is happening here? So we can consider a function. We say, let's take some polynomial P0. It's a low-degree polynomial, and write the first n/2 coordinates. We can write a completely different polynomial of low degree, which has, you know, nothing to do with P of 0. We know that these polynomials are very, very far from each other. So these polynomials will, this is something which is very far from being a valid code word. But what is our test? Our test just takes these consecutive points, right? Like we'll take this point and this point and this point and this point. So as long as we're not on the threshold, well, you know, we start with a point R in P0, and then, you know, we look enough deep points forward and we get into P1. And if we're not over there, then we'll never detect that anything foul happened. It would look like a low-degree polynomial to that test. And, you know, maybe in this picture, it doesn't, like, you know, make the point, because think about P0 huge and P1 being huge and D being quite tiny. So in that sense, like most of the probability is that you won't, you know, switch from P0 to P1. So just to say, okay, so by the way, if anyone has a better counterexample, I would, I see something in the chat, I would very much like to hear about it. But definitely this kind of like shows us for now that the test cannot work. And I want to say that this is something that happens quite a lot in research, right? Like we have an idea, it looks like nice, especially, I mean, I can imagine how this test came to be, right? Like we start with linearity test, we want to generalize it. So we try to follow the same paradigm, and then we hit some roadblock, something which seems, you know, like a real problem. But often the case is that the solution is just a tiny, very humble twist on that. So just curious, any thoughts or ideas? How might we, because like it seems annoying, right? It doesn't seem that something fundamentally breaks here, but rather, okay, so there is this annoying example of concatenating polynomials. So what would have been nice if we could have? Okay, so excellent. So as Hila is saying, you know, maybe we can choose these shifts at random, right? Like instead of just having them a plus 1, a plus 2, a plus 3, maybe if I can spread it around, maybe it could be, you know, a plus 2, a plus 4, a plus 6, or a 10a, 20a. Then if this is being chosen at random, I mean, you know, if it's like any one of them and it's fixed, then you can still, you know, instead of like putting the polynomials, you know, just P0 concatenated with P1, suppose the jumps are by 2, then maybe you can interleave it. But if you're choosing these jumps at random, then we should be good. And the beautiful thing is that this actually holds. So the statement doesn't only hold if we look at this constraint, but it also holds with nearly the exact same proof. If we do it for, you know, this Ci times f of a plus I b for any choice of b. So what does it mean is that we can kind of like choose the size of the jump. So we can either jump by 1, we can jump by 2, we can jump by 3, and it all would still work. And now this is nice. This means that maybe this could work, and indeed it does. So that's called the Rubinfeld-Sudan test. So we need Rubinfeld and Sudan, And what they're doing is exactly what we discussed. And we're just choosing these constraints completely at random. So let me say exactly what that means. We're sampling two elements, these R and S, and think of R as our starting point, and think of S as the shift, like by how much we're jumping each time. So what we'll do is we'll query F at R plus S, R plus 2S, and so forth until R plus D plus 1S. And we'll check that these local constraints are being satisfied. Okay, so that's the idea. The query complexity would be D plus 2. So we know still O of D. And let's see what happens. So maybe before we see what happens, at least like the definition of the test, does it make sense, the idea here? Any questions? Okay, I see that you're all nodding. Good. So
I have a question. So is it really necessary that we sample two random values? Wouldn't it be sufficient if we only take R and raise it to the power of I? Could this work?
That is interesting. My gut feeling is saying that this should probably fail. But I agree that it should definitely be the case that one can de-randomize it further. And maybe someone in the audience know better than me. I think there should be a way of de-randomizing it. So instead of like choosing 2 points, maybe you choose 1 point at random, and the other one you're using like pseudo-randomness, like maybe you choose some expander graph and you do a random walk on this expander graph, or when we use some other pseudo-random object. Potentially it could be an algebraic construction, like powering to something like that. So things like that could work. Yeah. And in some sense, formulated in the correct way, this could be an interesting research problem that one can see. How much further we can, de-randomize this type of problems and in what settings. Okay. So just to say completeness, as you get used to seeing pretty much throughout all of these calls and also the IP, completeness just holds by design, right? It's kind of like because we design a protocol and we want it to work. So it means that, we have a low degree polynomial, these constraints hold always, and therefore we will always accept. And now as for soundness, this is where we, as before, have to sweat a little bit. And we'll prove this theorem. Now, hopefully, when you see this theorem, it doesn't look as scary as it might have looked yesterday, because it is nearly exactly the same as what we had for linearity testing, right? Like we have this probability of our test rejecting. In the linearity setting, this means how many triangles were bad. And in our setting, it would mean how many of these, D tuples of constraints, how many of them are bad. And we want to say that this probability is kind of like, at least either half the distance of f from being low degree. Yesterday it was linear, today it's low degree. And here, yesterday we had 1/6, and now we have this dependency on D, on the degree, which is a bit, unfortunate, but, what can we do? Okay, and just to put it with some concrete parameters, suppose that f is 1/10 far, like 10% far from being low degree, then we will reject this probability of, 1 minus, they will accept this probability, which is most 1 minus O of 1 over D squared. So now here's a question to tell you, like, we started with this like nice, elegant test that we of just interpolating, which was natural and nice. And now we get a test which seems even worse, right? First of all, to begin with, we're losing a factor of 2 in the distance. The previous test, had just this term, and here we also have a factor of a half that we're losing. That's a bummer. And also, like this is kind of in a high agreement regime. And what do I mean by that? Like the we have this term, which is actually quite a bit of like a problem, right? Because it means that we can actually accept something which is far from being a low-degree polynomial with pretty high probability. Like maybe we'll accept this probability 90% instead of 1. Of course, this is not a real problem because, you know, we can just repeat this test and, you know, run it 100 times. And if all of the time it's accepted, then we know it's good. And if, you know, in one of them. So, but it does mean that, like, instead of making, you know, if we want to boost this error from 1 minus 1 over d squared into, you know, your favorite number, 2/3 or 90% or whatever, we need to repeat this test of d squared times, which means that the query complexity is all of this of d to the cubed. So, you know, so we designed a new test, which is far more cumbersome and more technically involved. It gets far less performance. So why do we do it? I mean, some would say maybe, you know, you want to send a paper to a conference and show that there is technical debt, but not really, right? And so the reason is that because this scales really, really nicely to the multivariate setting. Sorry. Just 1 second. Sorry for that. There's a vacation. Sorry for the interruption, the pleasure of having kids in a summer holiday. Okay, so the point is that this test will extend really nicely into the high dimensional setting, into the setting of multivariate polynomials. Okay, so let me continue. So first, just to what we are going to do in the next half an hour is to analyze this test and show that everything works really nicely. And in some sense, I think that the part until here was the important conceptual part. And what we're going to do in the next 30 minutes is kind of like, you remember the proof that we had yesterday? We'll try to go step by step, exactly as we did yesterday, and we'll see what are the modifications that we need to do. And in some sense, these won't be, you know, too sophisticated of modifications, but they do make interesting usage of you know, the properties of polynomials. So let me just like quickly remind you what happened in the linearity setting, because we'll have the exact same 3 claims. So the idea was, you know, we wanted to prove this theorem. So we started by saying, well, the number of bad triangles, number of violated local constraints is close to one particular function. And then we showed that, and this one particular function is not just an arbitrary function, it's kind of like the local correction of the linear function. Then we showed that the local correction, this plurality volt, is actually an overwhelming majority. And lastly, we saw that the plurality volt is actually a linear function. So what we're going to do now is we're going to say that the local, like, we have something analogous to this. We'll say the number of violations of these new constraints that we've seen captures the distance from the plurality volt. We'll show that the plurality volt implies overwhelming majority with respect to this constraint. And finally, we show that the plurality volt in our setting would be a low-degree polynomial. So we're really kind of monkeying the same design pattern of the proof. Okay, so let's do it. 3 parts for 3 claims. Starting with the first claim, which is maybe like the easiest. What are we doing here? We consider the notion of the plurality most popular vote. So what's happening here is the following. You know, we define this function g of f, and this scary-looking equation just tells us, look at the constraints and tell me each with respect to each value, which is the value that most of these constraints would lead to outputting. So to make it a bit more clear, so I want you to look at the gray part here at the top. what happens is that the constraints are of this form, right? It's like this linear combination which is equal to 0. And the first coefficient c of 0 is always 1. So in fact, the local constraint that we're checking, by just like moving the first term, it just means that the value at point R can be self-corrected by looking at this linear combination of other terms, right? So like if I want to find the value of x, it's enough to look at all of these shifts, combine them using the right coefficients, and they would give me a vote for x. And I can choose different shifts, and each one of them would kind of like tell me what is the actual value. So this is exactly what we're doing in this setting. And we want to say that if this thing is far from the function, then we'll reject with high probability. Or more formally, we want to say that the rejection probability of our algorithm, which checks these local constraints, is the distance from the plurality vote to the function. Now, do you remember what we did? Like, what was the idea of doing it yesterday? So what we did is we found this special set S of cases where we know we will definitely reject in that case. And we said, let's divide the probability. There is some chance we'll be in S, and then we can easily analyze it. And there is some probability that will not be in S, and then we don't care because this S will be big enough. So we'll do the exact same trick here now. So how the proof goes, we're choosing this S to be exactly as it was before, only with the new constraint. So what does it mean? It tells us exactly all of the points such that most corrections would not agree with the value of a point, right? So it's like a value x such that most of the shift would lead you to correct something which is different than the actual value, right? So pick your desired shift, and most of them would say, no, the value, right, we disagree with that value. And why do we do that? Because in order to bound the probability of our test rejecting, we can, as before, look at this scary looking expression, which is actually very easy. We can look at the case where R is in S, and then look at the quantity we care about condition on that. And we can also do, look what happened otherwise. We kind of say, in this case, that's hard to analyze, so let's forget about it. We'll lose a little bit, but we're fine with that. And then we're just focusing on that setting. So we know that, the probability of being in S is just the size of S versus the size of the field, just because we're using the language of probability to count. And, what is the probability that we will get disagreement, assuming that we're in S? So if we are an element of S, what is the probability that a random vote would disagree with the actual value?
Half.
Exactly, because this is how we chose the set S. We design it exactly for that reason. So we just get this quantity. And as before, as we had yesterday, we're observing that if if R is not in the set S, then definitionally it means that most of the values agree with it. And so it means that the correction, the plurality vote is exactly the function at this point. Like this is exactly how we define G of F. And so it means that the distance of GF to F is just determined by this point of S, and exactly as before, we get this claim, right? So this is the first claim. And as you remember, we had this like easy claim, hard claim, easy claim, and we'll have the same thing here. Okay, so let me continue. So if there is any question, please take your time while I'm sipping some coffee, and feel free to ask. And Matthias, regarding your idea, I'd be happy to kind of like talk about it later and see, maybe we can even like tweak it and make it work. That's it. Okay, so now we have the second claim. And the second claim, again, it's scary looking, but it's exactly what we had before. And if we say it in words, then it doesn't look so intimidating. It tells us that, the plurality vote is actually an overwhelming majority. right? Or it's like a rather big majority. And what does it mean in this setting? It tells us that, this is the plurality vote, and I'm checking what is the probability that a random constraint will agree with it. And we want to give some lower bound. So we had the same type of lower bound with linearity testing. Well, this amounted later, to a third, and then that thing was 2/3. So we want to show something like that. And now, if you remember, what we did is we kind of like got into the place where we applied some general, tricks for analysis of like functions, and we reduced the problem into understanding collisions. And we'll do exactly the same thing, only we'll have a lot of notation. So please don't be discouraged by the notation. It just, cumbersome, but it's not complicated. So here's the proof. We want to look at this quantity and we want to bound it. So how do we start? We do the same trick that we did yesterday, where we're not doing anything, but we're just like writing this in different words. We're saying out of all possible votes, which one is the most popular votes? Okay, that is easy. And now, let's see if I manage to make an impact. Can anyone tell me what's the immediate thing that we can do whenever we see a maximum or an L infinity norm?
On the L2 norm?
Yeah, exactly. So we can apply the trick that we had from yesterday, it kind of like tells that you can always bound the L2 norm by the L infinity norm times the L1 norm. Or in other words, if we, want to take a maximum, we can always replace it by just going here over like the L2 norm. And what happens when we're looking at an L2 norm? We kind of discussed this yesterday, that we actually have this expression of the form, sum of pi times pi, which is exactly what is the probability of having a collision, right? So again, lots of notation, but actually what is happening here is this: we look at this expression here, and we're saying, well, over some random s and t, random shift s and t, what is the probability that a shift by s and a shift by t would collide, right? Nothing different from what we had before. And the tricky part would be to kind of like bound this collision probability, which is what we'll do next. Before that, any question regarding this argument? Good.
Where exactly are you dividing by the L1 norm?
That's a good point here. Yeah, so okay, so in this particular case, it's maybe like slightly less clear to see it, but it gives you here like a factor of 1. So I mean, it doesn't affect here by like here it kind of like cancels out. It's a bit sneakier to see it here, but yeah. So, but if you just like sit down and write it and just like hold it. Okay, and here I'm again not trying to intimidate. So I just write this horrible looking expression, and I wrote such a similar horrible looking expression also last time. And the point is that what are we doing here is similar to what we had before. We're looking at some set with a cumbersome definition, such that if we have this particular, like if we have S and T shifts which are coming from this set, then we know we're good. So when you look at the definition of this, I don't want you to think about it at all, just like we define it now, so things would cancel out nicely. But actually, I'll show you that there is a nice geometrical intuition in addition to that. So let's do the following thing. That I just want to spend a minute talking about what is happening here, and maybe this would be helpful. So this is we're looking here at points, right? Like we say, these are, some conditions with respect, these are all of the possible jumps. And we start with a point R, and we want to jump by a factor of S. So what we're doing here is we take the standard constraint that we have, this type of constraint, And instead of applying it to a point R, I want to apply it to a point R plus IS. So what I get is the same constraint. I mean, it looks like a longer, uglier expression, but it's the basic constraint. Well, inside, we also have this expression of the size R plus IS. Okay, now you want to ask me, why, oh, why would I do that? I mean, it looks so cumbersome. So let me have some geometric like intuition. First of all, notice that when we're looking at this R plus I of S, this is a line equation, right? I mean, we start with a point X, and we choose another point Y, and then we take some scalar which runs between these 2 points. This is exactly a line equation. So for example, if we look here at the point X, so we have the point, okay, so this shouldn't be in X, this should be R, sorry. So we start with a point R, and we choose a direction S, and then we go 1 step in S, 2 steps in S, 3 steps in S, 4 steps in S, and we go this way. And we can also choose the direction T and go 1 step in T, 2 steps in 3, J steps in T. Okay? So when we're having this kind of like expression, you can think about it as walking 1 step here, 1 step here, and then walking in the other direction. And the cool thing about here is that we have this triangle, right? I mean, it means that we have a way of connecting this line and this line. And that would be the trick. So now let's see what happens formally. It's actually easier to see it algebraically without the intuition, but hopefully the intuition would help a bit. So what we'll say, we look at the constraint that we want to analyze, right? I mean, what we want to do, just remember, we want to show what is the probability of having this collision. And we're saying,
Tom,
yes.
Maybe can I ask a question? Because I think if I don't get this, cannot follow now. So I didn't understand. How did you get from the second line to the third line? I just don't see. It seemed to be an easy step, but I don't get it.
Yeah, absolutely, absolutely. You mean from the second
from the
line
square? Yeah.
to the third one?
Yes.
Absolutely. So what is happening here is, let me just like write it down. We had exactly the same thing before. Here we're saying we take a value and we want to know what is the probability that taking a random shift will hit the value V. But there is also a square, right? So it means that we have a certain probability Pi of hitting it, the value V once, and we also want the probability of hitting it again. So it's Pi. Think about like, Pi, the probability of hitting the vote I. So what is the probability of getting, what is Pi squared, is what is the probability that I take 2 independent votes and they happen to agree. And so writing it, I just like take the square and I write it just twice. So this is, what is the probability that this is equal to this is equal to V. And then I can just ignore the V because it's, it's just like equal to one another. Does this make sense? Think about it as in a birthday paradox. Like think about Pi, the probability of somebody having a birthday on the ith day of the year. And now what is sum of Pi squared? It's exactly the probability that, someone has a birthday on day 1, like 2 people have birthday on day 1, plus the probability of 2 people having birthday on day 2, plus so on and so forth. And so if you sum over all, I think it's the total probability of having 2 people with birthday at point I, right? So this is the probability of these 2 things.
Yeah, that helps, yeah.
Okay, good. But thank you for that question. It's important. It's an important step. Okay, so so recall that we want to look at this collision probability. So let's just write it down and try to analyze what happens. So, what I did here is just literally just applying the constraints again to f r plus is. So I'm looking at the constraint, and then I'm saying, let's look at, oh, sorry, not what I wanted to do. Here, okay, good. So I'm looking at this constraint, and I'm saying, let's look at the value of f. we can also apply the self-correction to this value. And so I'm getting the same expression, only here I replace f by the self-correction of f. And this means that I have to self-correct by some other element. Now what I'm doing is I'm just changing the order of summation. So instead of like going over in direction, like instead of taking step in direction I and then in direction J, I'm taking the other way. So I like to view it as a walk. You know, I start here in R, I'm taking some steps here, and then I go here. And I say it's the same as like starting here, taking steps towards the data direction, and then back here. We'll still reach the same point. And why do I do that? Because that would exactly give us like the probability of, like this would exactly give us the correction according to the other point. So this is exactly a collision. So it means that if we chose S and T, which happen to fall in that set that we define precisely for that point, then we'll have the collision that we want. And all that is left to do is kind of like to say, what is the probability that we will not have a collision? It means at the very least, it's kind of like we can all, like at the very worst, it's the probability of us not falling within this set. And what is the probability of not falling within the set? So if you remember yesterday when we talked about linearity, the probability of not falling into the set was, just what is the probability of having two random triangles being bad. And here we have exactly the same thing, just with more notation. It's just like, what is the probability of two random shifts being bad, which is exactly the constraints that we're checking. And the reason why we have this factor of 2 times d plus 1 is because the number of constraints that we're actually checking here, even though I wrote it as 2 equations, it's 2 equations, but this holds, but the constraints refers to, for every I in 1 to d plus 1. So we have d plus 1 constraints here and d plus 1 constraints here, and that exactly gives us what's going on here. Okay, so a lot of notation. When you look at this slide as it's written right now, it just looks off-putting, but in fact, it's just more notation with respect to the same idea. Okay, and now this gets us to the last part, which remember it was like easy, hard, easy. So this is the easy point, the last step. So we want to prove the theorem that I wrote there above. And we had, this is just a reminder regarding how we define the plurality correction. And we proved these 2 claims, right? Like first the step 1, which tells us that if we want to see what is the probability of rejection, it suffices to look at one particular function, the function which is like the plurality correction. And we also saw that this plurality correction, in fact, the agreement is more than just that. And what we want to do is okay, so we want to prove the theorem. So remember last time we had this if things are great, if the rejection probability is greater than 6, then we're done. So here we have it with respect to this number. And again, this is not because what we want to do, but rather we wrote here these restrictions because we don't know how to deal with this situation. So we're saying, if the rejection probability is greater than that, then like we're happy. That's the best that we can hope for. And otherwise, let's do a little bit of work. So we assume otherwise. Okay, and just maybe it's worth to mention that we assume otherwise, and this implies that the distance the moment that I write it down, so this entire expressions become 1 minus 1 over 2 to d over 2, which is what we want to prove here. Okay, so just syntactically, at least everything makes sense. And now we want to prove that under this construction, the function gf is in fact a function of low degree. And then, we are done as before, right? Because we want to prove that the rejection probability is at least a distance from gf, but gf is a low degree function, and so this gives us also a lower bound on this function. And as yesterday somebody pointed out that I had a typo, and this should be a bound. So also today I have a typo, and this is a bound. Just to show you that these slides were made by taking the original slides and changing them to make the more complicated case. Okay, so the formal claim that we want to make, which again looks a bit complicated, it's actually very simple. It says that if we have this condition, if the rejection probability is not too much, if we don't have too many violations, then what will happen is this condition will always hold. And if condition always hold, then by the characterization, this is a function of flow degree. Okay, so I see here a question. So Amit is saying correctly regarding, yes, that this is like that the two sides of the parallelogram fix the fourth point. And I see another question regarding for d equal to 1, should we get the same result from the soundness analysis of BLR? So that's an interesting question. I'd imagine so, but maybe we will get some slackness because this is a more general type of, I mean, it would definitely get you something, but perhaps because we're in a more general setting, this would not be as good. But it's a nice thing to check. Okay, so let's just finish this claim. So again, here is a horrible definition, which again, just we designed, this was, yesterday it was the set T, which is a case where we can easily, we say that if we're in this case, then we're easily done. So what is happening? We define this set, and don't worry about too much what the condition says, but like even, let me just try to say quickly, but we're saying that we will want to look at the correction at a certain point, and we want to say whether it agree with this other correction. It's a correction of correction. Well, let's take it first as just as a technical step, and then we'll see what happens. So in this case, if we want to look at this term, which is what we want to show that is equal to 0 for every RNS, I should say that we're fixing here an RNS, and we want to show that this would be equal to 0. So we want to show that this is 0. So how do we show that? So first of all, we write this, and we do the same trick that we did last time. So I take this expression as is, I'm taking GF here, and I'm writing the correction at that point. And then, exactly as in the last step, we're just switching the order, and again, walking on the parallelogram, we're just like switching the order in which we sum over J and I, and we end up at the other point. But now what we have is a condition which we know is being equal to 0. And why is that? Because we chose it so. So we defined it exactly this way. So if you think about it, this horrible looking definition was what's happening when we want to say, when would this be equal to 0? So we write down an expression that would be a satisfying condition for that. So this is why it looks, so cumbersome. Okay. And then, we can do union bound as we did before and say, what is the probability that this thing would not be 0? Well, it's exactly upper bounded by us not belonging to that special set. And as before, because the special set is being chosen, it's a random condition, it's a random violation of the interpolation condition, then each one of them holds exactly with this probability as we chosen. So yeah, it's a bit gritty, but if you go over it later with the notes and do it step by step, you see that it's exactly as we had before. It's just a bit harder to see because admittedly, this slide is very, very, very dense in notation. Okay, so hopefully that wasn't too much of a pain. And let me kind of like conclude by something interesting, which is, so far we just have a bad test for a univariate case, which doesn't achieve what we, wanted to get. So let's actually get reap what we saw. And we want to kind of get to extend it into the multivariate setting. So the point is that the local characterization in the multi-dimensional case, it holds exactly like analogously. So what I mean by that, we have this exact same statement, and the only thing which differs from the local characterization that we had before is what is drawn in blue. So we know before we had one dimension, now we have to the power of n, and now before we had the polynomial in one variable, now we have polynomial in n variables, but the same condition holds. In fact, in some sense, it's even a nicer condition when we think about it in higher dimensions, because what do we have here is just like saying we pick a point A, we pick a point B, and we go through all of the points in them. So this is, like just like ax plus b, just like the line equation. So we just check lines, and we kind of like say that there exist coefficients. So another way of looking at it is saying that in low-degree polynomials, you can look at every line and say that there exist coefficients that would make this line 0. Okay. Other ways in the order of quantifiers, but never mind. Okay. So the test would also be exactly the same. So I just, this is like a copy paste of the previous one, and the only thing which changes that the degree is to the power of n. Query complexity, because of that, remains O of d. But now this is fantastic because the size of the object is d to the n, and because it's like n-dimensional, but we only look at d out of it, so it's much, much, much smaller. And yeah, as we said, it's just, it's a random line test. It's just like, so the actual thing that we do, the test would be, we look at the cube, we take one random line, and we then interpolate this line and check whether it's this line is of low degree. So think how nice is that? It tells us that if you want, a multivariate polynomial, if you want the cube to be far from low degree, then in some sense, the way that it would be far is propagated everywhere. You remember that I had the silly slide of this, piece of bread with a bit of jam? So this is precisely that, because it means that if you want to be far from low degree, you can't concentrate it. It's just like one corner of that cube. But rather, every line, or like the vast majority of lines, would be affected by this corruption, right? So like if the bad points are the jam, then low degree polynomials do exactly that, and each line would kind of get that. Okay, so just to say that the theorem from Soundness, it looks exactly similar, and the proof is exactly the same up to adding, to the power of n everywhere. So it's the absolute exact same proof. You have it in the notes, but you see that it's absolutely the same. Yeah, and then all we have to do is repeat a test of d squared times, and we get a low degree test with query complexity of d third, which is completely independent of the dimension. So the higher the dimension, the happier we are. Okay, so it seems that we managed to survive through all these calculations and heap of notation, and hopefully you got some nice ideas from it. I wanted to maybe conclude by saying that low degree testing, it's not just like a nice paper from '96, but rather this is a very active field of research to this day. If at some point you might have heard about the big breakthrough that we had in quantum computing, that MIP star result equals RE, then this all strongly relies on a low degree test that holds in the quantum setting. And in fact, there are dozens and dozens of papers which deal with various notions of low degree tests in different regimes and different settings. And that's a very active and vibrant field of research where you make these technical improvements and you can get some important results. Yeah, so I hope this was interesting, and tomorrow we're starting with something which is completely different. I mean, it is in the same, high level theme, but technically it would be completely different, and we'll see this it would be a non-technical conceptual lecture where we'll see a lot of nice ideas of how we can deal with testing polynomials, which are univariate, and do it locally. Now, we might say that we started the lecture by saying that this is impossible, but we'll do what we typically do in math when a problem with something is impossible. We change the setting a bit. So next time we'll change the setting, we look at PCPs that allow a bit of interaction. And using this interaction, we'll be able to do something which a priori seems completely impossible, which is to test univariate low-degree polynomials in a very efficient way. Okay, thank you very much, and see you tomorrow. I'll stop the recording.